Okay, so what we are drawing is, let me just repeat. So these are the set of relations we had got for scattering when we were studying scattering from periodic solids, and we get exactly the same kind of conditions for electronic states when there is a degeneracy between free electron energy levels. And you can view this as sort of physically, I mean, the electronic waves getting scattered at the Bragg planes. And Bragg planes, as I said, are bisectors of the reciprocal lattice vectors. Is it okay now? Yeah, it's recording. So I'm drawing the reciprocal lattice. So I started with a free electron situation, but then there is a lattice because of which there is a weak periodic potential. And because I have a lattice, I have a reciprocal lattice. So I'm drawing these things in the reciprocal space. This is the origin. This is some G. This is, minus G. I'll have a 2G. I'm drawing this in one dimension. This is another reciprocal lattice vector, and so on. And the bisectors of these vectors are the Bragg planes, right? So if this is G, halfway to this is where I have a Bragg plane. Similarly, halfway to this, I have a Bragg plane. So this is G by 2. This is minus G by 2. And so on. So I'll have this, and then I'll have this. There'll be a Bragg plane here, there'll be a Bragg plane here, and so on. Now, what did we learn? We learned that, okay, now that I have a reciprocal lattice, and we learned that these band energies, epsilon k plus G is equal to epsilon k. These are periodic functions in the reciprocal lattice. So if I have this parabola around the origin, I'll have the same parabola around G, and they'll be degenerate here. That's the degeneracy we are talking about. And in one day, you can only have two-fold degeneracy, but in higher dimensions, things can get more complicated. So now you understand what is this degeneracy that we have been talking about for so long. So, and I'll have the same parabola around minus G and so on. And it is these points of degeneracy where the splitting would take place in a weak periodic potential. So what will happen is this will get split, and you will get this. And this splitting would be twice of UG. So all right. So if now let us refer to the pictures given in the book, which will be easier for me. So the panel A here is the free electron parabola. And then when I have a periodic potential and the corresponding, the periodic lattice and the corresponding reciprocal lattice, this parabola is repeated around, they call it K, I call it G. So here is the degeneracy we are talking about on this Bragg plane. And there is a splitting, which is equal to twice of UG. So what I can do is, so basically this gets split here. Okay, so this is this branch, and then there is a splitting, and the parabola continues here. So there's a discontinuity. And similar thing would happen at every Bragg plane. So half K is a Bragg plane corresponding to the lattice vector, let me call it G. Half G is the Bragg plane corresponding to the lattice vector G. G is a Bragg plane. This would also be a Bragg plane corresponding to the reciprocal lattice vector twice G. Similarly, this plane here at 3/2G would be a Bragg plane corresponding to the reciprocal lattice vector 3G, and so on. So all of these are Bragg planes. So there will be discontinuities. Here it would be twice of UG, here it will be twice of U2G, here it will be twice of U3G, and so on. So this parabola now gets split into these various branches. But then these band energies are periodic functions of the reciprocal lattice. So I can translate all these branches back into the first zone here. So remember, Wagner's side cell of the reciprocal lattice is the first Brillouin zone. So in this 1D lattice, this region from -12G to G, -12G to half G is the first Brillouin zone. So I can translate these by appropriate amounts, that is integral, reciprocal lattice vectors back into the first Brillouin zone. So for example, this branch, let us look at this branch. If I translate it by -G, this point would go there, this point would go there, and this entire branch would come here like this. So this is, if you follow my pointer, this is exactly this thing, this piece translated by -G. Similarly, this thing here, this branch, is this one translated by G this way. So then I get this. And then if I move this by, I have to move it by G. So for example, I have to move it, this is G, this is 2G. So I move this by 2G and this by 2G this way, and I'll start getting this branch. So what I get, so this branch is this one. The one above this one would give me this branch. This one and this one would give me this branch, and so on. So eventually what I get is, so this is my first band, this is my second band, this is my third band, this is my fourth band, and so on. So I'll get this within the first Brillouin zone. So let me repeat. So this piece remains here. When this thing is translated by -G and this thing is translated by G, I'll get this piece within the first Brillouin zone. Similarly, this one translated by twice G and this one translated by -2G would give me this thing here. So I have band 1, band 2, band 3, and so on. So one parabola now in presence of the periodic potential gives me these bands within the first Brillouin zone. But then, so this picture, when everything is plotted, everything is drawn within the first Brillouin zone, is called the reduced zone scheme. I can repeat all these branches in all the Brillouin zones. So we'll come to the concept of higher Brillouin zones shortly. But I basically here what it means is that I can have a similar picture, but then because these are periodic functions, I can keep this and translate this by 2G and draw that also. I can keep this, translate it by G and draw that also. So then I'll have all these pieces, all these bands drawn in all the Brillouin zones. So that is this picture. Okay. This is called the repeated zone scheme. So this picture is called the extended zone scheme picture. This is the reduced zone scheme picture, and this is the repeated zone scheme picture. But they contain the same information. But it's good to keep in mind that band energies are periodic functions of reciprocal lattice vectors, and that will be important in the subsequent discussion. Okay, so one thing is that we have one parabola, which was one parabola in a completely free electron picture, now gives me this kind of band picture, and also it introduces band gaps. Okay, so this continuity, remember we talked about continuity of the electronic energies as a function of K. Now suppose you start from K equal to 0, you are increasing K and you are here, let's say in this band, the energy goes like that. There's a maximum, then it comes down, then it becomes 0. So when you are here, it remains a continuous function as long as you are within this same branch or the same band. If you cross band, of course, there is a discontinuity in energy. It's a different energy here. So this is one band. I could label this by n equal to 1. And this is another band. I could label it with n equal to 2 and so on. So n has to be the same for epsilon to be a continuous function of K. If I go to a different n, then of course there are discontinuities. Right. So one can try to view similar things, band structure starting from free electron bands or free electron energies in higher dimensions, 3 dimensions. That quickly gets more complicated, so we'll not get into this. So what we'll now discuss is the idea of Brillouin zones, and in particular higher Brillouin zones. So what is a Brillouin zone, or what are higher Brillouin zones? So I'll show you this picture. This is a very nice tool on the Wolfram website. Okay, so it's a little slow, so it will take me some time. So what we have here is a square lattice in 2D, and things are best explained in 2D because 3D will be very complicated. So suppose we have a square lattice on 2D. So the reciprocal lattice would also be a square lattice. If the square lattice has sides A, the reciprocal lattice will have sides twice pi over A. So suppose this is the origin of my reciprocal space. This is a reciprocal lattice vector from here to here that would have length twice pi over A. This is also length twice pi over A, and so on. And bisectors of this, so this one, for example, would be a Bragg plane, and so on. So now what I can do is, this is my origin, so I can draw lines from this to all the reciprocal lattice points. Okay, and so each one of those will be some reciprocal lattice vector. I can draw perpendicular bisectors of those. Those are the Bragg planes. With that construction, I'll show you that. I'll have a set of points which are sort of closest to the origin, closest to this point than any other reciprocal lattice point. And that is shown by this red area here. So this red square here is the first Brillouin zone. This is the Wagner-side cell of the reciprocal lattice in this case. So here, this red one is the Wagner-side cell, and this is the first Brillouin zone. Now, what I do is I look at points which can be reached from the origin by crossing only one Bragg plane, but no more. Then I'll have these regions. Okay, and if you look at this region, this triangular region, these points, this set of points is closest to this point in the reciprocal space than any other point. Similarly, points here are closest to this point than any other point, and so on. And this entire region, although it's a disconnected region, this sort of brownish shaded region, can be reached from the origin by crossing one Bragg plane. You need to cross one Bragg plane to reach these points. So these pieces taken together constitute the second Brillouin zone. It'll just show us the second Brillouin zone only in a while. Yeah, so that's the second Brillouin zone. Similarly, and it's very easy to visualize here that the second Brillouin zone is also a Wagner-side cell. One can mathematically prove it, but I'll not get into that. But by translating these pieces by appropriate amounts, by appropriate lattice vectors, you can bring these inside this, and they will exactly fill this space, this square. If you translate these pieces appropriately, they will. It's very simple, right? Because if you translate this triangle by G, so it will come. This will come here. This will go there, and this will go here. So you will have this part covered. And by symmetry, you translate this by an amount G downward, this triangle by an amount G upward, and this to the right. So they will exactly fill this square. And so the second Brillouin zone is also a primitive cell of the reciprocal lattice. And similarly, we can look at the third Brillouin zone. So it will come in a while. Yeah, here. So these are the pieces of the third Brillouin zone, and so on. So again, you can try to figure out that by moving these pieces by some reciprocal lattice vector, appropriate reciprocal lattice vector, they would exactly fill this. Sorry, the first one is not drawn here. They will exactly fill the square that is the first Brillouin zone. So the third Brillouin zone is also a primitive. So all Brillouin zones are primitive cells of the reciprocal lattice. And the point is that, so the definition is that the nth Brillouin zone is such that you can reach points in that Brillouin zone by crossing n-1 Bragg planes, but no fewer. You have to cross at least n-1 Bragg planes to reach the region or reach the points that constitute the nth Brillouin zone.
Sure.
Yes.
Why is this yellow colored boxes the third Brillouin zone?
Because to reach there, you have to cross two Bragg planes. So I start from the origin, I cross one Bragg plane, then I cross another Bragg plane, and I reach here. So two Bragg planes, so it's the third Brillouin zone. No Bragg plane is the first Brillouin zone. One Bragg plane, it's the second Brillouin zone. That's just a definition.
Oh, and what will be the next Bragg plane?
Next, Bragg planes. There are all kinds of Bragg planes. So this one is, these are all equivalent. So these are Bragg planes, right?
Yeah.
These lines. Then you have these lines that are Bragg planes. In fact, if you want to see Bragg planes, just wait for a few seconds. It will show you all Bragg planes. So the idea is that you connect the origin to all reciprocal lattice points. Okay, all points on the reciprocal lattice. See, these are all,
Yeah.
quickly gets complicated. So these lines are all Bragg planes. So this line, for example, would be bisector of this point, the vector from this point, which is the origin, to this point, I guess. So this is the bisector. So you start from the origin, connect to all reciprocal lattice points, and then draw their bisectors. So those are the set of Bragg planes, and there are an infinite number of them.
Yeah, I just thought that because for the first two zones, the Bragg plane sort of coincide with the boundary of the zone.
The boundaries of any Brillouin zone, the boundaries are given by some Bragg planes for sure. So even for the third Brillouin zone, so for example, if I look at this piece, okay, this is a boundary, this is a boundary, this is a boundary, and they are all Bragg planes. Of course, the boundaries are given by Bragg planes because these regions are created by the Bragg planes.
So the next one would be just on top of that, just on top of the yellow triangle.
On top of the yellow triangle, I don't understand
Like
what
if you
exactly
could
you
move
mean
your
by that.
cursor a bit higher.
Here?
Yeah, the shape just above this. Yeah, this part
Yes,
would be the
yes,
fourth.
yes. This would be part of the fourth Brillouin zone. Yes, this one, this one, this one, and so on. I think there is a. Let me see if there is a picture in the book. Yeah, here. Just give me a second. I'll show you. Yeah, here. First Brillouin zone, second Brillouin zone, third Brillouin zone, fourth Brillouin zone.
I see.
Fifth, sixth, and so on.
And all of these are equal area and map up to the primitive thing.
Yes, yes. So you have to move for nth Brillouin zone. You have to identify all the pieces, all the disconnected regions that form the nth Brillouin zone, translate them by appropriate reciprocal lattice vectors, and they will come inside this so that they move into the first Brillouin zone, and they will exactly fill that space. So these are all primitive cells taken together, right? Okay.
Yeah.
Any other questions? All right. So then what we now do is, one important sort of use of this is figuring out the structure of or shape of the Fermi surface of metals. So what we do is, so now I showed you what this sort of idea of Bragg, the Bragg planes and the Brillouin zones are, the higher Brillouin zones. So now we will use this to see if we can construct Fermi surfaces of real metals. not free electron metals that do not experience any potential at all. So the starting point is, of course, the free electron Fermi surface, which is a sphere, as we studied in the Sommerfeld model. And then put these Bragg planes, and keep in mind that near these Bragg planes, the bands, the energy bands get split, as we just discussed. So we'll distort, or we'll introduce discontinuities in these in the free electron Fermi sphere near the Bragg planes. And so then these pieces that we get after that will constitute the final Fermi surface, or the free electron, what are called free electron Fermi surfaces of the metals. So what is the prescription? So I'll show you one or two pictures because it quickly gets very complicated. Let me see which one I wanted to show. Just give me a second. Yes, so this is one of the things that I wanted to show you. So what we are looking at, see, I cannot draw this, and there are hardly any better pictures than this. This is roughly what you would get. So you try to get the idea, because it's not possible to create these things by hand. So I'm just trying to give you the idea behind what is drawn here. And in the end, we'll extract one very, very useful idea. So what are drawn here? So what we have is an FCC metal. So we have a metal in an FCC structure, which has 4 electrons per atom. Okay. So we can construct its unit cell. So if we think of the conventional cubic unit cell, there are 4 atoms in the unit cell, in the cubic cell. So 4 atoms would give me 16 electrons and so on. So if I have, knowing the cubic lattice constant, I know the electron density, right?
Sir, your voice got cut. So can you please repeat?
Yes, I'm repeating. So we have an FCC lattice. We have a metal forming an FCC crystal, okay? And we know the cubic lattice constant, A. If I describe an FCC lattice by the conventional cubic cell, I need 4 atoms in the unit cell. So I need 4 atoms in the cube to describe an FCC lattice. Is this statement clear to everyone, that we need 4 atoms? Yes or no? If you do not understand why, let me know.
Yes, sir.
Okay. So 4 atoms. So let's say each atom has 4 electrons. Each atom has 4 valence electrons. So that makes it 16. So I have 16 electrons per cube. Knowing the cubic lattice constant A, I know the electron density. Knowing the electron density, that is N in my Sommerfeld picture, I can calculate Kf, Fermi sphere. So in the reciprocal space, I know what my Fermi wave vector is, what Kf is. So a sphere with that radius will be my Fermi sphere in the completely free electron picture. Now comes the reciprocal lattice. I mean, now comes the effect of the FCC lattice, the corresponding reciprocal lattice, which is a BCC lattice, and the corresponding Bragg planes. So you put the Bragg planes in place, and what they will do is they will cut this Fermi surface at some point, some regions, and the Fermi surface then will see, Fermi surface is nothing but parts of electron bands. So they will, the Bragg planes would introduce discontinuities of this nature at the Bragg planes. So what was a continuous spherical surface will now get discontinuous at the Bragg planes. And what are shown here are different pieces of that. So the panel A, for example, okay, before that, the other thing is that if you have 4 electrons per atom, the free electron Fermi surface extends up to the 4th Brillouin zone. Now, this is something one can work out, but just take my word for it now. So you have a sphere which extends into the 4th Brillouin zone. It crosses the 2nd Brillouin zone, so which means that the sphere has parts of the surface of the sphere exist in the 2nd Brillouin zone, in the 3rd Brillouin zone, and in the 4th Brillouin zone. But it's bigger than the 1st Brillouin zone. So there is no part of the free electron Fermi surface within the 1st Brillouin zone. This is just a geometrical thing. I mean, there's nothing terribly, complicated about it. Later on, I'll show you 2D example. So if I have an HCC lattice with 4 electrons per atom, the free electron Fermi surface is bigger than the 1st Brillouin zone. So there is no part of the Fermi surface, free electron Fermi surface within the 1st Brillouin zone. So the Bragg planes that define the boundaries of the 1st Brillouin zone, they do not intersect this free electron sphere. So we don't need to worry about them. But the sphere has parts, the surface of the sphere has parts in the 2nd Brillouin zone and the 3rd Brillouin zone. So the boundary between 2nd and the 3rd Brillouin zone would cut this surface, and the boundary between the 3rd and the 4th Brillouin zone would cut this surface. Okay, so figure A shows you parts of the surface in the 2nd Brillouin zone. You see how complicated it gets. And then what has been done is that these parts which exist in the 2nd Brillouin zone have been translated back into the 1st Brillouin zone by appropriate reciprocal lattice vectors. And that gives you this kind of a surface. So this is the panel C here is in the reduced zone scheme. Everything is drawn in the 1st Brillouin zone. So this shape, this outer shape that you see here is the 1st Brillouin zone corresponding to the real space HCC lattice. This is the bit in the 3rd Brillouin zone. Again, these pieces have been translated back into the 1st Brillouin zone, and this is what you get here. And these are the pieces in the 4th Brillouin zone, some small bits here and there. So the point here is that even the free electron Fermi surface, starting from a free electron sphere, and then cutting it appropriately at the Bragg planes, and translating things back into the 1st Brillouin zone, if you want to, gives you parts of the Fermi surface that looks pretty complicated. So the Fermi surface of real metals are pretty complicated. And but nevertheless, these are useful constructs. So this bottom row here shows you the branches. These are called branches of the Fermi surface. So this comes from the 1st band, this comes from the 2nd band, and this comes from the 3rd band. These are branches of the Fermi surface that are obtained from different Brillouin zones, but here all are shown within the 1st Brillouin zone within what is called the reduced zone scheme. Now, one important and interesting point here, and this has very, very important consequences for electrodynamics in crystals, is that this surface here, panel C here, this surface encloses states that have higher energy compared to the states outside it. So this surface encloses states that are unoccupied, whereas states outside it are occupied. Now, how is that possible? Well, that is possible because we have obtained this surface by translating some surfaces from the higher Brillouin zone back into the 1st Brillouin zone. So it is difficult to visualize this in 3D, and that too in a complicated thing like an FCC crystal. But I'll give you a 2D example to illustrate the point. So when you have such situations that you have a part of the Fermi surface, you have a branch of the Fermi surface, which encloses states that are of higher energy compared to the states that are outside it, those states are called the hole states. They don't have electrons, they are not occupied by electrons, and they are hole states. And many of the sort of anomalies encountered in the Drude model we'll see can be explained if we consider these hole states that will come to later on. But this idea of hole states is very, very important. Okay, and just to sort of complete the story, I'll show you another figure from the text. So this, for example, these are branches of the Fermi surface of an HCP lattice formed by a divalent metal. So there are 2 electrons per metal atom, and it forms an HCP structure, like, for example, magnesium. And then you have the Fermi surface looking like this. Okay, so that's about Fermi surface. So let me now give you this 2D example. It's not clear, right?
No.
One second. I'm having difficult. Now it is okay. Should be fine. Okay. Why is it? Okay. Can you see it clearly now? I hope so.
Yes, sir.
Okay, so let us consider this example in 2D to illustrate the point. So let me try to draw a slightly better figure. So, suppose this is the first Brillouin zone of a square lattice. And it turns out that if you have a divalent metal forming a square lattice, it's an ideal situation, but let's take it for example. Then you can calculate what its the radius of the Fermi sphere, which is a circle in 2D, would be. And it turns out that it just goes out of this square. So you will have something like this. So this was the original free electron Fermi surface. Then you have this first Brillouin zone because of the square lattice. So you will introduce discontinuities here. So apart from this slight change in shape near the boundaries, so basically it will go like this, okay? So it will be like this part will be like this, and so on. So you get the idea. So then these are the branches. So this. These come from the second Brillouin zone, and these ones come from the first Brillouin zone. In the free electron case, of course, all the states within this circular region were occupied. So let us mark them. So all these are occupied, and the ones outside are unoccupied. Then let us draw the branches separately within the first Brillouin zone. This is my first Brillouin zone. So the part that comes from the first band is this, right? And these states are occupied. These are these states within the Brillouin zone and within this. So these are the states, and they have lower energy compared to states outside. Then let us draw the other piece within the first Brillouin zone. So what do I have to do? This piece is outside the first Brillouin zone, so I have to translate it back here. So this thing would come here. This thing translated up would go here. This thing would come here, and this thing would come here. So I'll get these pieces. Now in this, which are the states that are occupied? See, these were occupied. So when I translate this by some reciprocal lattice vector downward, these are the states that are occupied. Similarly, when I translate this, these are the states that are occupied, these are occupied, and these are occupied, and this is my origin. So if I consider these surfaces, the states within are unoccupied, and outside them are occupied. So when you have situations like this, whether you have a surface, states within the region enclosed by the surface are occupied, and the states outside are occupied, you call that electron line. And this is a hole-like Fermi surface. So this branch is a hole-like Fermi surface. And as I said, this is a very important concept, and we'll see that some of the anomalies that were observed, for example, in Hall effect in some metals like aluminum, for example, can be explained if we take into consideration these hole-like states in their electronic structure. And in semiconductor physics also, this holes play a very important role. So this idea is very, very important. All right. So I think that.
Sir, how are you getting the?
Yes.
Sir,
go ahead.
How are you getting the hole-like zone?
Let me repeat it. So you understand this picture, right?
Yes, sir.
Now, so from this you see that I have two branches of the Fermi surface. One branch is formed by these surfaces. I have drawn that here. See, once the splitting is done, these are pieces that come from the first band. So these are those surfaces. And states here inside this are occupied. So these are occupied. So these are surfaces that enclose occupied states. So they are called electron-like surfaces. On the other hand, look at these branches. I mean, this branch, with these pieces. So I want to translate this thing within the first Brillouin zone. So what do I have to do? Remember, here to here is the length of a reciprocal lattice vector. Okay, because this is my origin. I have a reciprocal lattice point here. I have a point here, and this is the sort of bisector of that. Similarly, this is a bisector because this is a Bragg plane. I have some reciprocal point in the reciprocal space here, and so on and so. So this much is a reciprocal lattice vector. So I translate this by this reciprocal lattice vector to get it here. This thing is obtained from this by translating it up here. This space is obtained by translating this here, and this is obtained by translating this here. So if you want me to draw, so I call this 1, 2, 3, and 4, and so 1 comes here. This is 1. 2 comes here. This is 3. And this is 4. Those are those pieces. Now, if I look at these surfaces, remember, this is the origin of my reciprocal space. So they enclose a region but then these states are occupied. And these states actually have come here. So these are unoccupied. So they are enclosing a region which have unoccupied states, whereas outside that region, there are occupied states. So that kind of a situation is called a hole-like Fermi surface. Okay. Right. Is there any other question? So shall we move on to the next topic?
So would you explain the graph again slightly?
This one here?
Yeah.
Okay. So let me move these things. Okay. So to start with, I have a 1D lattice. With some lattice constant A. This is real space lattice. Corresponding to this, I have a reciprocal space lattice, which is also, just a 1D chain of atoms, and it would be twice pi over A. So I'm drawing that here. So my G, this is my origin. So this length would be twice pi over A x, and so on. Similarly, I have a minus G, which is the same thing here in this direction. So these are my points in the reciprocal lattice at G, 2G, and minus G, and minus 2g and so on. And perpendicular bisectors of each reciprocal lattice vector is a Bragg plane. So I have a vector from here to here, g. So this line at g by 2 is a Bragg plane. I have a vector of length 2g here. So half of that at g is a Bragg plane. I have similarly have a vector till 3g. So this thing at 3g by 2 is a Bragg plane, and so on similarly in the other direction. Okay, now when I have this periodic lattice, this was my original free electron parabola with this. By the way, these relations are called dispersion relation, how energy changes with k. So I have a parabolic dispersion here. Then I have introduced this periodic thing. So I can view this parabola as being repeated at g and 2g and so on. Because epsilon are periodic functions of in the reciprocal space with periodicity of any reciprocal lattice. So whatever I have drawn around 0 here, I can draw around g here and 2g here and so on. So this will give me this degeneracy. So this parabola and this parabola, they would be degenerate at g by 2, right? That's obvious because k squared and equal to k minus g squared when k is g by 2. So that's the degeneracy you have here. And similar degeneracies would occur at other Bragg planes. That's what we discussed just before this. Then what we sort of learned from that analysis is that at these Bragg planes, this degeneracy is lifted when u is non-zero but weak by an amount which is twice of 2g ug. So these energies would split and become like this. In fact, you can even calculate that the slope of these curves would be 0. It's done in the book. It's just simple derivative. So basically what you have to do is you have to take this, and you can find that when q is a vector on the Bragg plane, the slope would be 0. So that is that construct. So at each Bragg plane, this twofold degeneracy is lifted. You have one upper branch, one lower branch, or what we call one band here, the other band here. Similarly at every Bragg plane. Does that explain it?
Like, what should we state as the cause for this split?
Q, the periodic potential because of the lattice points or the ions sitting at the lattice points. That is that Q. That is the origin of U.
Yeah. Okay.
Yeah. So it's important to realize that just this weak periodic potential can, or even, when we studied Bloch's theorem, for example, that behavior of single electrons, and there's no electron-electron interaction. We are not getting into that complication. Even behavior of single electrons in a periodic potential gives you very rich physics. And so this band structure is that, and this band structure gives you that explains that some things are metal, some things are sort of semiconductors, some are very large gap insulators, and so on. And the amount of band gap determines what the sort of electron dynamics is in these materials, and so on and so forth. So this idea, and these are all consequences of the fact that electrons are moving in a periodic potential. So understanding and appreciating band structure is very, very important, whatever you want to do next. Okay, so now I'll erase this and then I'll go to a different topic.
Sir,
Yes.
here we are just saying that at different reciprocal lattice points there are parabolas. So each parabola is continuous. So then summation of all those parabolas should also be a continuous function. So why are we getting discontinuities at g by 2? And,
No. See, the parabolas are not wave functions. The parabolas are just energies. You can't sum over energies, right? If you have degenerate wave functions, their linear combination is also, if you have degenerate eigenstates, their linear combinations are also eigenstates. But we are talking about energy here, not wave functions.
they are kind of potentials, right? So
they are electron energies. They are electron energies.
Oh, okay.
Epsilons. These are plots of epsilons. Look at the picture that I showed you in the book, which sort of explains this difference, how the splitting comes and different schemes like reduced zone, repeated zone, extended zone. So it's important that you understand. So what we do here is epsilon as a function of k, and I drew one parabola around 0, the other around g, and so on. So this is epsilon. Epsilon as a function of k, which is a periodic function when I translate it by g. Therefore, I can translate this parabola by an amount g. That's what I used.
Sir, we can still think of these energy states in just first Wigner side cell, right? Because when you are calculating the energy, the wave functions, we made an argument that we can bring any wave vector to the first Wigner side cell, right?
Right.
So we don't have to give this argument of periodicity. We can just consider the energy levels in the first Wigner side cell.
Yeah, we can do that, and that's exactly what I did later, right? So then if this is my g, if this is my minus g, then so these are my in 1D. I'm drawing in 1D. So here to here is my first Brillouin zone, and so then I drew this, right? Sorry, it would be that. So the free electron levels would look like this. It's a bad drawing, but nevertheless. So we can translate everything back into the first Brillouin zone. So, go and look at that figure in Ashcroft. You will get it in any textbook, but Ashcroft and Mermin's book, figure 9.4, which I just showed you a little earlier. So I can translate everything back into the first Brillouin zone, and I'll get these bands, which are just pieces of the same parabola after it is sort of made discontinuous at the Bragg planes. Yes, what next?
Yeah, so this was also the reason for translating the Fermi surfaces to the first Brillouin zone.
Yes.
Okay.
Exactly.
Yeah.
I can translate everything back into the first Brillouin zone. I can keep them over all Brillouin zones. I can translate them back into the first Brillouin zone or whatever. I mean, all three schemes are equivalent, and you just do whatever is convenient in a given situation. So what we have been doing here so far is that we have been trying to calculate how the bands or the Fermi surfaces of metals look like, starting from the free electron picture. So the starting point so far was the free electron picture, and then we sort of tried to study the effects of this weak periodic potential on it. And as we saw that in most of the Brillouin zones, nothing happens to the free electron bands except at the Bragg planes, where their discontinuities are introduced when there are degeneracies. Now we sort of want to shift gear completely and approach the problem. So one thing we know that whenever electrons are moving in periodic potentials, they have to satisfy the block condition. So that is a very general theorem that we proved. And they would form bands. So these were very general statements without referring to free electrons or anything. It's just a consequence of the fact that electrons are moving in periodic potentials. So we should be able to construct these wave functions and calculate their energies starting from atoms, because after all, it's the atoms which are sort of assemble to form solids. So rather than starting from this free electron plane wave function, e to the I k dot r, like things which we did in case of metals, and they make sense for metals because we have this sort of intuitive understanding that electrons are free to move around in metals because they carry electricity so easily, they carry heat so easily, and so on. So this is a good starting point for metals, but this need not be the good starting point for everything else. And whether it's a metal or a non-metal, semiconductor, whatever it is, after all solids are constituted of atoms. So atomic wave function. So what if we want to calculate all these quantities, the electronic wave function, that is the band wave function, their energies, and so on, starting from the atomic picture? Okay, so that is the idea here. So the basis, so to say, the basis so far for us was the plane waves. We were expanding the band states in terms of plane waves. So we wrote psi of k as a function of r as sum over g. So these are plane waves. Instead, we now want to use these atomic wave functions as our basis. So this approach.
Sir, the screen is actually stuck.
So this approach is called the tight binding approach or the tight binding model. Okay, so as I said, so we have a crystal Hamiltonian. This is the Schrodinger equation for the crystal Hamiltonian that we need to solve. So we'll do it for solids, but before that, let me just try to introduce some ideas. So let us talk about a more general case. So what we are doing is, I'm just dropping all these indices in K and so on. So I'm expanding this wave function as a function of, as a linear combination of okay, so let us try to understand what these are. So this phi so there is an atom at the location Ri, capital Ri. There is an orbital phi a, one of the atomic orbitals on that atom. We call that phi a. So that is phi a, and we construct linear combination of such atomic orbitals to give our wave function in whatever system we are studying. It could be a solid. Eventually, of course, we are interested in periodic solids. It could be even a molecule. And in fact, we'll first take the example of a molecule. So, so we assume that phi A's are known exactly. And by the way, knowing phi A's exactly for multi-electron atoms is also not a trivial job. It's not like solving the hydrogen problem. It's an interacting electron problem. So in real situations, these are also rather complex tasks. I mean, as complex as finding the wave functions of electrons in solids when you consider electron-electron interactions. But anyway, so but here we pretend that we know phi A's exactly, and so then this equation, so we'll just plug this thing in. So I have okay. So then what I do is we take scalar products with some atomic orbital B. Phi B at so on both sides, we take scalar product with some orbital phi b located on the atom at Rj. This should be R minus Rj. Okay, so what do we have on the left? What we have on the left is some matrix element of the Hamiltonian when these phi A's are considered to be forming the basis. So this would, apart from these coefficients, this integral would give me a matrix element. So let me write the notation that I have used here. there was a sum over AI and CAI. Okay, so what are these quantities? This is just the matrix element of the Hamiltonian. So and these quantities are this is H and S's are just the overlap integrals. Okay, are you able to follow the board clearly?
Yes, sir.
All right. So I'll just do a slight change in the notation here. Instead of writing A as the dummy index and B as the free index, I'll just interchange it. That's just a convenience that I used earlier. So basically, I can write this equation here as so these are the equations that arise when I use these atomic orbitals as my basis functions to expand whatever I have here, whether the band states or the molecular orbitals in the molecule, whatever I have. And this approach in general is called linear combination of atomic orbitals, or so this particular approach here. This is called or the LCAO approach. Okay, so that's what we get. And then what, so generally this, these things are not calculated from the known atomic wave functions, even in the more sort of most realistic calculations of with tight binding. These are never calculated sort of ab initio. So what often is done is, in a tight binding approach, these are considered as fitting parameters. So you may have some information about the system you are interested in from whatever, from experiments, from some other kinds of calculations which are not tight binding. For example, one could have done a band structure calculation for a solid or some other calculation for molecules. And fitting these as parameters to sort of match those results, you extract these quantities. So, all right. So there are, I'll take a simple molecular example, and to illustrate sort of the different types of terms that you encounter here. And then next time we'll take up the discussion of periodic solids. So suppose I have, so what I'm trying to say here is that these are often fit to experiments or so these are parameters for us, or sometimes they're just left as parameters, and you still can get information and qualitative information about a class of systems at least. So now let us take an example. The simplest case is a diatomic molecule. It could be H2 or LiH or something like that. So here we need to consider only the minimum that we need to consider are the two s orbitals on hydrogen. So the two 1s orbitals on the two hydrogen, or the 2s orbital on lithium and the 1s orbital on hydrogen, and so on. So we have a situation where I can expand my molecular wave functions as a linear combination of two orbitals. And there are two atoms. So I'll get a 2 by 2 problem here. So, so basically, if I want to write this in matrix form, what I'll have is see A, B, both are 1. And since each atom has only one orbital on it, so A is synonymous to Ri and B is synonymous to Rj. So they will not give us any extra indices. So H11 minus epsilon, because we are assuming that the orbitals on each atom are normalized. So when A is equal to B, this S is 1. So I'll pick up an epsilon here. And then the off diagonal things, I'll have H12. Similarly, H21, which would of course be H12 star, Hermitian. So that's that equation for a diatomic molecule in which each atom has one orbital on it. I'll now erase this part. Let's make a simplifying assumption that we neglect the overlap integral. So we neglect these to make matters simpler. So then So now you can go ahead and solve it. You'll have, this part has to be, the determinant has to be 0 for you to have non-trivial solutions and so on. So you can write epsilon as I'll write what delta epsilon is. And you will have this two things, C1 or mod C1 squared Okay, where alpha p is related to delta epsilon. So what are these various quantities? H11 is when A is equal to B. So it's the matrix, it's the diagonal matrix element of the Hamiltonian. So it's a diagonal matrix element of the Hamiltonian. These are called on-site energies. But remember, this is diagonal matrix element of the Hamiltonian. So look at this, when A is equal to B, it's the matrix element of the full Hamiltonian of the diatomic molecule here. In the state, let's say on 1s orbital on one of the hydrogen atoms. So it is not the orbital energy of a single hydrogen atom. It isn't, because the Hamiltonian is not the Hamiltonian of a single hydrogen atom. This Hamiltonian contains terms coming from the other hydrogen atom also. So for example, the Coulomb interaction due to the nucleus of the other hydrogen atom is also included in this Hamiltonian. So although we call it on-site energy, this does not depend on the atom on which this site or this orbital exists. It depends on all other atoms also. So in that sense, it's a sort of not strictly an on-site term, although these are called on-site energy. So this is a common mistake or common misconception that may happen if you are not aware of these chemical bases of this tight binding model or tight binding Hamiltonian. So H11, H22, etc. are called on-site energies, and if the atoms are the same in whatever system you have, for example, if I have H2, then the two hydrogen atoms are equivalent. So therefore, I'll have H11 equal to H22, and in that case, this delta epsilon would be 0. So delta epsilon is called polar energy. So as you can imagine, if delta epsilon is not 0, you have bond polarity. If delta epsilon is 0, it's a perfectly, it's just a covalent bond with no polarity. You get two different solutions, bonding and anti-bonding states. Alpha P related to delta epsilon is called, it has some name. What is it called? Bond polarity. And if you have this as 0, you will have, I have to check this. No, okay. So I have written mod C1 square. That's okay. So you will have C1 is equal to C2 is 1 over root 2. And for bonding state, and C1 minus C2 for anti. So I have these diagonal matrix elements, H11, H22, etc. Then I have this off diagonal things, H12, or equivalently H21. So those are called covalent energy in the molecular context, and these are in the context of solid state. These are more commonly called as the hopping integrals. So this hopping integral or hopping terms is a very common terminology in this tight binding model. Okay, so that's the basis of this tight binding model. The basic idea is that we are using now atomic orbitals to expand our molecular, or next time we'll see how to use this to expand the band wave functions in a solid. So I think we'll stop here today and take it up from here next time. Are there any questions?
Sir, sir, when we expand psi with basis as the atomic basis using the atomic orbitals, so ideally we should take infinite number of them. But when we take just 1 or 2 orbitals, so I mean, are the expansion legitimate?
No, they aren't legitimate in the sense that they do not form a complete basis set. No, they don't.
Yeah, I mean, then is the I mean, will the results be valid?
What do you mean by valid?
Valid mean, I mean, the expression that we used to write the matrix equation. So before arriving there, ideally in the summation we had, I mean, in the summation over B, we should have infinite number of orbitals. But when we take just only a small part of that infinite matrix, I mean infinite n by n matrix, so there will be errors in the value of energy.
Of course, there will be errors in the value.
Yeah, I mean, so so here
you know what the biggest thing is. This is just so. If you ask me about this particular analysis, it just sets the conceptual framework. The biggest thing here is that there is, I mean, if you ask me what would be the numbers, now from this analytical calculation, we cannot calculate numbers. or the best we can do is, well, what I'm trying to get at is that even to explain existence of a stable H2 molecule, you have to take into account the electron-electron interaction. And that's a complicated thing. So what am I trying to say? What I'm trying to say is that we will here work in ignoring the electron-electron interaction. So if you ask about, if you want to answer questions like how is that a H2 molecule is stable, or how does its energy change as you move two atoms apart? In other words, if you want to calculate dissociation energy and things like that, that is not going to be what you can get out of this simple analysis. On the other hand, it does set a conceptual framework, and eventually we will use it to study simple solids. And again, as I said, certain conceptual things you can get pretty well out of these. For example, you can get the fact that when we get to solids, if you have a half-filled system, by half-filled you mean you have exactly half the electrons, half of the maximum number of electrons that you can put in a system, you get a metallic state, and so on. So there are things that you can get, there are things you cannot get. Yeah, if you ask that whether it's strictly rigorously true, it isn't. But then in any real calculation, you have to include electron-electron interactions. And when you do that, you have to do things on a computer. And when you do that on a computer, you cannot use an infinite basis set. It has to be finite at some. So there are several issues in this.
Okay, sir. Sir, another question is that in the example, we used only one atomic orbital. So which one should we use?
Which one we should use? For hydrogen, it is obvious, right? It's the 1s orbital. You should be, so what are you interested in? You are interested in describing the bonding and chemical sort of properties of whatever molecule or a solid, or see, all the important things or most of the important things happen because of the valence electrons. Most of the things we will be interested in happens due to the valence electrons. So it's the valence orbitals that one should be looking at, not the ones that are completely filled and what are called core orbitals, which do not take part in bonding, or something, or orbitals that are not occupied, much higher in the energy. Those are not going to play important role in bonding, subsequently transport, magnetic, etc. properties of molecules or solids. So therefore, if it's lithium, the first thing I would do is I would include the 2s orbital.